Hi, I'm Saul Friedberg, and this lecture is to give background in preparation for my lecture in the Field's Number Theory seminar on extending the theta correspondence. So I'm going to be talking about three topics, and the three topics are the following. First is about theta series in the Weil representation, which might sound familiar, and I'll say a bit about the connection to Steve Kudla's talk just in a minute. And then the second thing I want to spend some time talking about is metaplectic automorphic forms and covering groups. And you might be familiar with the word metaplectic because, of course, it comes up in the context of theta series in the Weil representation. But I want to talk about metaplectic in an extended sense that includes that, but goes beyond that to some other cases. And I'll try to also make the tie between this language of metaplectic automorphic forms and very classical objects automorphic forms that transform by some homomorphisms that you may not have seen before, but that are very number theoretic. The third topic that I'd like to talk about is Fourier coefficients in unipotent orbits. And Fourier coefficients come up in the context of automorphic forms on groups that are bigger than GL2, where there are different unipotent groups you could integrate over that would mimic a classical Fourier coefficient. And we need to drill down a bit and understand some aspects of that to really have a good language to talk about different kinds of Fourier coefficients. So that's what's on the agenda for today. And then at the very end, I'll give a few references for further reading and just say a word or two about them. Okay, so to begin, part one is about theta series in the Weil representation. And as I mentioned, that material came up as well in the lecture in June 2020 in the seminar by Steve Kudla. And in fact, his background slides also had a section on theta series in the Weil representation. And I've linked to that. You'll find that if you upload the PDF or if you download the PDF of my slides, so you can actually click on this link and get right to them. And I'll describe this independently, but I do encourage you to review the notes, roughly the first 12 pages or so of Steve's slides as well. Okay, so to begin the treatment that I'll give here, let's start with W, a symplectic vector space of dimension 2n over a number field F. So symplectic means that it's equipped with a non-degenerate antisymmetric bilinear form that's F valued on W. Antisymmetric means that if you take the inner product of X and Y, you get the negative of taking that same product applied to Y and X. The word reversed gives you a negative sign. And then we introduce in a standard way the symplectic group, the set of all automorphisms of W, which have the property that they preserve the symplectic form. So GX paired with GY is the same as XY for all X and Y in the vector space W. So that's one of two groups that are going to be important in my talk. The second group that's going to be important is the Heisenberg group. And just working over F for the moment, we can realize that group as taking the vector space W and making a direct sum with one copy of the field F, and then introducing a group operation, a multiplication. And the multiplication is given as follows. I take X comma T, where X is in W and T is in F, and I multiply that times yu by simply adding the vectors x plus y, so the vector space addition gets used. And then in the second entry, I take t plus u, I add over the field f, but I also adjust that by the pairing of x with y with respect to the symplectic form. Okay, now SPW, of course, X on W, we set it up to be the set of all automorphisms of W that preserve the symplectic form. And it also acts on the Heisenberg group by simply acting on the first coordinate. So G applied to XW is GX, G applied to XT is GX comma T. And because of that, we can make the semi-direct product of the Heisenberg group with the symplectic group, and that's the operating object that will be important in a lot of what I do in my talk. One last comment on this slide, that we can view these groups as algebraic groups over F, and so we also can talk about their idyllic points. We could talk about their points over any local field as well. Okay, now there's one more group that's going to be important in the context of theta series and the Weil representation that comes up, and it also I think implicitly came up in Steve's talk as well, and that's the double cover of SPW, and that's the classical metaplectic group, a term coined by Weil. And since it's a double cover, you can think of it as a set of pairs where G is in SPW adelic, and then there are two of them, so epsilon is either 1 or -1, and then there's a multiplication. And on the first coordinate, it's just the usual multiplication. But when you want to figure out the way the multiplication works in the second coordinate, you introduce a 2 cocycle, and that 2 cocycle has a bit of an elaborate story. And classically, over a local field, it might be called a Rao cocycle. And so there's a reference I'll give at the end of the lecture today where you could find out more information about it. But we'll just take this as the natural ambient group. And one other thing to mention is that if you put the identity for the first entry, so G is the identity, and let epsilon be plus or minus 1, you get a group of order 2 that's central. Okay. Now we also can take the semi-direct product of the Heisenberg group with this double cover, the metaplectic group. We can do it adelically or over some other field, like a local field. Okay, now besides the groups, there's one other decomposition that I am going to be concerned about, and that's that this vector space W, which remember has dimension 2n, breaks up as the direct sum of two n-dimensional spaces, where those spaces W plus and W minus have the property that they're maximal isotropic. So remember, isotropic means that the pairing of two vectors in that space with respect to the symplectic form is exactly 0. All right, so I'm going to start with W and that decomposition as well. And then there's some group theory which really underlies theta series, and it was explained by Weil. And so to say it here, let psi be a non-trivial additive character of the adels that's trivial on F. And then there's this Weil representation, which I'll call omega psi, and it's a representation of that semi-direct product that we met of the Heisenberg group with the double cover of the symplectic group. And it's an infinite dimensional representation. It's realized on a space of functions, and those are the Schwarz-Brucha functions on W plus of the adels, this adelic vector space. Schwarz-Brucha at infinity is rapidly decreasing, and there's a full definition which I won't give, which you can look up, but you might, morally speaking, think of this as a space of rapidly decreasing functions that are good to use for adelic constructions. And this representation, in fact, in this specific realization is called the Schrodinger model. And there were some formulas that were presented for it on the 5th slide of Steve Kudla's talk, maybe not with the most general symplectic group, but certainly with SL2. And you can get the flavor for the way that group acts on these rapidly decreasing functions by means of those slides. Okay, so that's all the structure that we need. And then the adelic version of theta series is this. I'm going to make a function of G, which is in the Heisenberg group semi-direct product with the metaplectic group, adelic again. And the way I'll do that is I'll start with G, and I'll let G act by the Weil representation on a rapidly decreasing function phi on a Schwarz-Brucha function, and that'll give me a new Schwarz-Brucha function. And then I'll add that new function up over all W in the maximal isotropic subspace W plus, but the F points of it, not the adelic, but the F points. Okay, so that's the definition of a theta series. And again, F is discrete inside of A, so I'm summing up over a discrete set, which would be analogous to summing up over a lattice in a classical language. And the notation here, the parentheses 2, is meant to remind us that we're on the double cover of a symplectic group. And the reason for using that is later in the talk and in my actual lecture, there will be higher degree covers as well. I'll carry around the dependence on the choice of additive character. And when I use these in my actual lecture at the Fields seminar, I won't carry around the test function phi. I'll say we'll look at a space of these thetas, and that's the variation on phi, but I will keep track of the 2n, which if you remember is the degree of the vector space W. And so in that case, the symplectic group could be realized if you choose the basis as 2n by 2n matrices over F or over the adels of F. Okay, so that's why I'll put the 2n in there to remind us what the group that we're working on is for that SPW. Okay. Now, this theta series is automorphic, and that means what it usually means, which is to say if you take not adelic points, but rational points, H of WF, symmetric product SPWF, then in fact the theta series is invariant. If you change G to gamma G, you get the same thing. And that invariance, that automorphicity, is behind the ability of using these theta functions as integral kernels. And that was exactly what Steve Kudla did in his talk. And it's against the classical theta correspondence that you do such a thing. And it all works because you have an automorphic form and you integrate against a kernel, which is built out of theta 2. And that kernel is automorphic as well, invariant under the F points. And that's what makes all the things make sense. Okay, so that property is true in this context. Okay, just one more slide about theta series in the Weil representation. We're going to view these theta functions as living on adelic groups in my talk, but I think it's good to know that you can really relate these to classical objects that go back to Eichler and Siegel. And this is, was explained in Steve Kudla's slides, so I invite you to review that. And it's maybe worthwhile to keep in mind that these theta functions are all generalizations of the Jacobi theta function, the sum of e to the pi I n squared z. And that Jacobi theta function is good to keep in mind because that theta function has a property that it has lots of Fourier coefficients that are zero, the ones that aren't squares. And in some sense, that's the signpost to something that's true for more general theta functions, maybe not in exactly the same way. Morally speaking, theta functions should have lots of Fourier coefficients that are zero, and that's something I'm going to flesh out later on in this preparatory talk. Now, the classical Jacobi theta function gets analyzed, say, in Riemann's second proof of the functional equation, essentially, by using Poisson summation. But if we didn't have the Weil representation or Poisson summation to capture its properties, we could get them in a different way. These theta functions are related to residues of certain Eisenstein series, and so we could learn the automorphicity from the properties of the Eisenstein series. And that relation is not trivial, and it's really a significant special case of a Siegel-Weil formula, and that formula also made an appearance in Steve Kudla's talk, and it's in Steve Kudla's slides. So that connection between Eisenstein series, and more precisely the residues in this case, and these theta functions is also going to be something to keep in mind for my talk. All right, now working over any completion of F, there's also a local Weil representation, and that will play some role when we talk about local theory. All right, I'd now like to go to part 2 of my talk. Part 2 concerns metaplectic automorphic forms and covering groups, and we already met the double cover of the symplectic group, so now I'd like to go to higher degree covers. So let me fix R greater than 2, and I'll be telling you about the R-fold cover. And let's let F be a number field containing a full set of R roots of unity, which I'll write as mu sub R. Okay, so there are distinct R roots of unity sitting inside of F. And then there's something that comes up in algebraic number theory. You define something that generalized the classical quadratic residue symbol, and namely that's the Rth order power residue symbol, C over D sub R. And this symbol takes values not in plus or minus 1 like the classical object would, but rather in the Rth roots of unity. And if you want, you can think of it as taking values in an abstract group of Rth roots of unity, or you can fix an embedding of mu R into C cross and think of it as taking values inside of C cross. Okay, now what I want to do is tell you that this C over D sub R, this Rth power residue symbol, also turns out to have a homomorphism attached to it. And that's something that might not be as well known as it could be, but it's an old fact due to Kubota. And Kubota proved the following. Let's start with SL2 of the ring of integers of my field F and look at the principal congruent subgroup mod R cubed, or if you want, modulo the principal ideal generated by R cubed. Okay, so that's a subgroup of finite index, just given by some congruence condition. Kubota showed that if I take a matrix in that group, A, B, C, D, and I attach to it C over D sub R if C isn't 0 and 1 if C is 0, then I get a homomorphism. And that's not a trivial fact. In fact, the proof makes use of reciprocity. But given that fact, there's something that's very natural to do. We know we're used to looking at automorphic forms that transform by means of a character, chi of D, and why not try to look at automorphic forms that transform by means of kappa? So those are the objects that I'm going to be concerned with. A metaplectic automorphic form for GL2 in this sense is a function f, which is automorphic under gamma, transforms under gamma in this congruent subgroup by means of the character kappa. F of gamma g is kappa of gamma f of g. Now, to be a little careful about it, what does G mean here? G has to be in R2 copies of GL2C if I think of functions on the group. And if you want to go to the symmetric space, you would think of R2 copies of hyperbolic 3 space. R2, of course, the number of pairs of complex pairs of embeddings of F into C. And the action of the coordinates is some kind of a Hilbert modular type action, if you wanted to phrase it in that language. Now, where are covering groups in this? Well, it turns out it's easy to check that the kernel of kappa is not a congruent subgroup. So it's fundamentally a different kind of character than sending D to chi of ABCD to chi of D, where chi is a Dirichlet character, because that kernel is a congruent subgroup. But here, the kernel is not a congruent subgroup. And if you want to take a function f like the one I had on the last slide and describe it by means of an adelic function, you can't do so directly. And if you will, the problem is that if you're going to describe kappa, when you make the translation of the adelic language, you would want to introduce the maximal compact subgroup of SL2 of the finite adels, and you would want a character whose kernel is of finite index in that maximal compact subgroup and is not only a finite index, but is a congruent subgroup. And you can't do that because the kernel is not a congruent subgroup. So you have to actually do something a little different. You can't build these functions into functions on the adel group in a straightforward way. And instead, what you do is you change the group a little bit. You introduce the notion of a covering group to describe these automorphic forms adelically. And I should say that this isn't a radical idea. This already comes up when you try to talk about modular forms of half-integral weight in the adelic language. And you already have to look at the symplectic group, the metaplectic group in the sense of A, or Shimura introduced a covering group of this nature in describing modular forms of half-integral weight in his classic paper. So what we're doing when we look at these covering groups is something that's been done for a long time as a way to handle these things. And just by the way, if you think about the classic half-integral weight modular forms, which transform by CZ plus D to the 1/2, they do transform by something like C over D sub 2 epsilon D inverse CZ plus D to the 1/2, the theta multiplier. And so that C over D sub 2, the quadratic residue symbol, is really built into the theta multiplier as well. And if you were writing down a theta multiplier without real embeddings, you wouldn't have a CZ plus D to the 1/2, and then something like this theorem of Kubota would be true even for the twofold power residue symbol as well. Okay, back to general groups. I want to take this construction and generalize it. So let G be either the local or adelic points of a nice algebraic group. And the kind of thing that I'll be concerned with in this talk are covers of G, where they fit into this exact sequence, covers of G by the group of rth roots of unity, G superscript parentheses R. And I won't describe them all that carefully. They'll say a little bit more in the next slide. But if I were just to describe them by means of group extensions, to describe a group extension, you need a 2 cocycle. And here I could build it from local cocycles, and those local cocycles involve rth order Hilbert symbols in their definition. And then to make them adelic, it turns out there's a bit of a story there, and the Kubota homomorphism plays a role. But the study of these extensions is a very natural thing. And in fact, these extensions have quite a long history. And I want to emphasize that the number theory is built into the extensions. They're built out of rth order Hilbert symbols, and reciprocity plays a role in making the adelic extensions. So there really is number theory just in the very construction of these groups. Okay, now what about bigger groups than GL2? Well, the news is that Bass-Milner-Serre extended the Kubota map to a wide class of groups. And they did it in their fundamental work on the congruent subgroup problem. And in fact, that was the key to solving the congruent subgroup problem. So they introduced homomorphisms on congruent subgroups gamma contained in G of OF, where G is something like a symplectic group or a special orthogonal group. Those will be the cases that I'll be concerned with. You can also do some exceptional groups, in fact, but that's not going to be relevant for us. So I'll take a symplectic or orthogonal group, and there is a congruent subgroup, and you can extend the homomorphism kappa to find a homomorphism from that congruent subgroup gamma to mu r. But the kernel of kappa is not a congruent subgroup. So these kappas are not that mysterious. In fact, if you think about embedding SL2 into a bigger symplectic group or a special orthogonal group, at least if you're doing it with respect to a short simple root, then in fact kappa would on that embedding would basically be the same as what you would match the Kubota homomorphism that I already showed you, that C over D sub r are 1. And there's some small adjustment you need to make for the long roots. Okay, so those are the objects that I'm going to be concerned with. And again, these adelic extensions that I introduced on the last slide are necessary if we're going to try to discuss automorphic forms on G that transform with respect to the Bass-Milner-Serre homomorphisms that arose in this classical work on the congruent subgroup problem. And now I can tell you the key problem that I'm going to talk about in my talk. Namely, the theta correspondence is this very important construction in the theory of automorphic forms. But the question I'm going to address is, can we extend it to work on automorphic forms that transform not by a Dirichlet character chi of D, but transformed by these Bass-Milner-Serre homomorphisms, which are exotic, their kernels are not congruent subgroup. And we'll see that we actually can make a theta correspondence for these exotic automorphic forms that transform by this character that is built in a fundamental way out of reciprocity. All right, so that's it for part 2. One more subject for my pre-talk, and that's about Fourier coefficients and unipotent orbits. And this is language that we need to work with larger groups than just GL2. So the goal is to talk about, in a systematic way, Fourier coefficients of automorphic forms on groups such as general linear groups that are larger than GL2, symplectic groups, and orthogonal groups. So let me tell you the prototype of a Fourier coefficient. That's the Whittaker coefficient. So here's what I'll do. I have an automorphic form, say phi on GLN, and I'll integrate against the full upper triangular unipotent subgroup. So that means matrices that are upper triangular and have ones on the diagonal. And I will integrate against I'll integrate against that subgroup U against a character of that subgroup UA mod UF. And a character has to be trivial on commutators. And when you unpack that a little bit, it turns out that a character of U could only see the diagonal that's just above the ones. So that's entries like U12, U23, up to UN minus 1n. So why not just add them all together to get an element of the adels and take a standard character, an additive character of A that's trivial on F. Okay, so that's the kind of thing that we'll be doing. Now, one thing that I've done, which is a little bit different than what happens classically, I'm not getting a number. I've left this G in there, so I'm getting a function of G. And that turns out to be something I've done by design. So what you should do is think of these Whittaker coefficients that I just showed you, this function of G, as a generalization of a classical Fourier coefficient. But you might object. I mean, when you do classical Fourier coefficients, you don't integrate against just psi of x if you're looking on GL2 and 1x01 is the upper unipotent. You look at mx. So I could look at all characters of the form psi of m1 u12 plus m2 u23 plus dot 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 plus mn minus 1 un minus 1n, where these m's are, if I were doing it classically, elements of, say, OF or some inverse different or something like that, okay? So that's the kind of thing that you would expect me to do, but I don't need to do that. And the reason is because I kept the G in there. So if I wanted to go from the coefficient where all of these are 1 to this more general coefficient, it turns out that if you just change G to T times G, where T is a diagonal matrix in GLNF, and you make a variable change and use that phi is automorphic, so F point things in the F points of the group pull out, then it turns out that all these Fourier coefficients are already built into this function W phi of G. So they're already there. I don't need to do anything separately for them. Okay, so that sounds really good, but there's a complication. If I go beyond GL2, the group of upper triangular unipotents is no longer abelian. So you can't just conclude because you've taken all the Fourier coefficients that you can reconstruct the function from them. And so it's not obvious that you can reconstruct phi from the knowledge of its Whittaker coefficients. It does turn out to be possible for cusp forms on GLN, but that's not true actually for other groups like symplectic and orthogonal groups. You can't always do that. And in particular, it turns out that there really are automorphic forms that are not zero, but where every single Whittaker coefficient is zero, or if you will, this function W phi of G, this one function, is identically zero. Okay, and yet the function is not identically zero. That actually even happens on GLN if you go outside of cusp forms, but look at some other L2 functions. You actually can find such things. All right, well, what are we going to do? It could be that all the Whittaker coefficients are zero. And in that case, I'd like to suggest that that means we've averaged over so much that we're getting zero. So maybe we should shrink the group U we're integrating over. And we should maybe look at some smaller groups and characters that are generic for them and look at those instead, because we want to make something that's non-zero to have something to talk about. So the groups that you might look at are, roughly speaking, described by the Jordan decomposition, and the language that people use is the language of unipotent orbits or sometimes coadjoint orbits. And in my talk, the fact is that all these objects can be described by means of partitions. If we're on GLN, they'd be partitions of n. So I'm going to index unipotent orbits by partitions. And so that's why you'll see partitions coming up in my talk, and they're describing classes of Fourier coefficients. Okay, so there's a recipe. If you give me a partition, I can write down explicitly the unipotent group that's attached to it, and I'll give it on the next slide with an example on the slide after. It's really for completeness. But the key thing I think it's important to remember is that there are bunches of unipotent groups. And so these unipotent orbits form a partially ordered finite set. So the largest element would be the full unipotent radical of the Borel subgroup. That's the maximal element of this partially ordered set. And there happens to be a minimal element as well. But beyond that, if I give you, if you give me two unipotent orbits, I might not be able to compare them. Okay, I'm also going to be working with covering groups, that double cover or that R-fold cover, and the same exact definitions apply to covering groups because it's a theorem that every unipotent group can be canonically split inside of a covering group. So you don't need to do anything different. These notions basically go over, without any change, they go over essentially verbatim, unus mutandi to the covering groups. Okay. So now just for the record, I'm going to tell you if you give me a partition, a bunch of numbers R1 up to RK that add up to N, how I can make a specific unipotent group that's attached to that. So here's what I'll do. I'll take the R1 and I'll attach to it a bunch of powers of T to the R1 minus 1, T to the R1 minus 3, and keep going down by 2 until I get all the way to a negative T to the 1 minus R1. And then I'll do the same thing for R2, T to the R2 minus 1, T to the R2 minus 3, on down to T to the 1 minus R2. And I'll just keep doing that for R1, R2 up to RK. I get a bunch of powers of T. I'll take those powers and rearrange them into a diagonal matrix that I'll call HO of T. And it's the diagonal matrix which has those powers of T, and they're set up to be non-decreasing as you proceed down the diagonal. So you either get equal or lower powers of T as you go down the diagonal. All right, so here's the group U, O, that we attach to this. What we'll do is we'll start out with a full upper triangular unipotent group, and we'll conjugate it by this matrix HO of T. And when you do that, you'll see that different entries in that unipotent group pick up different powers of T under that conjugation. And so you'll get T to the J, where J could be 0, 1, 2, or so on. And for the unipotent group UO, I will only take the J's, which are 2 or more. And that will turn out to be the group that I'm going to want. So here's an example. I'm going to do SO5 for you, and I'll take the partition 3, 1 squared. 1 squared means repeat 1 twice. And then the diagonal matrix. So the 3 gives me a T squared, gives me a T squared, a 1, and a T to the minus 2. The 1 gives me a t to the 1 minus 1 t to the 0. So there's a 1 there, and there's a 1 there from the 1 squared. And then I've taken these entries and I've rearranged them so I'm going from highest power of t down to lowest power of t. Okay, and then the instruction is that I'll make the unipotent group by conjugating and only taking the entries which pick up a power of t that's 2 or more. So the x would pick up a t squared, and the y would pick up a t squared, and the z would pick up a t squared. But these entries where there is a 0, they would have a 1 and a 1. So when I conjugate, I would not pick up a power of t, in fact, at all. I get t to the 0th power. If I was doing this in Geo, I would have other entries in those start entries, but in fact, if I'm in the special orthogonal group, then those entries are automatically determined by the ones I've shown you, so that the whole matrix is in the special orthogonal group. Now, in fact, in order to make a matrix that's symplectic or orthogonal, you're not allowed to use all partitions, say of 5 here. So there are some conditions, parity conditions, that are necessary for the partition to be of symplectic or orthogonal type. Okay, now I want to tell you how to take this unipotent subgroup UO and attach some Fourier coefficients to it. And we'll do basically what I already described. So I start with O. I take this UO, its associated unipotent group. And then there's a notion of a generic character, psi UO, which I'm not going to describe for you exactly, but it is worth saying that there can be more than one conjugacy class of psi UO, so it's a little different than the Whittaker case where you only needed to look at one. Here you might need to look at more than one conjugacy class. Nonetheless, there are some generic characters attached to O, and what I'll do is I will take the Fourier coefficient of phi with respect to one of those generic characters by integrating phi, translating it by u and putting in a character, doing a Fourier coefficient kind of thing to do, and integrating over UO of adelic mod UO of rational. So those are the Fourier coefficients attached to a unipotent orbit. Now I mentioned that loosely speaking, the theta functions constructed from the Weil representation, well, again, you can think of them classically as Steve Kula explained as well, though they have lots of vanishing Fourier coefficients. Well, when you look at it in this language, you can check that all the Fourier coefficients attached to non-minimal unipotent orbits with respect to that partial order on the orbits, all those Fourier coefficients are 0. The only ones that live are the Fourier coefficients that are attached to the minimal unipotent orbit. So that's a precise sense in which a theta function has lots of vanishing Fourier coefficients. That's not a property that you usually see. And in fact, in general, if you look at say some other automorphic form, then you might want to look at its Fourier coefficients. And it's an interesting question to understand exactly which maximal unipotent orbits or orbits conceivably an automorphic form phi might have, for which it does have non-vanishing Fourier coefficients. But in the theta series case, it's only the smallest one that appears. Okay, one more slide and then just some references. The one more slide says that you can do the same kind of thing locally. And if you do it locally, so now I might start with pi v and say irreducible admissible representation of a p-adic group, then instead of a Fourier coefficient, what you do is you look at a twisted Jacquet module with respect to the group UO over the local field F and a character psi UO. Okay, and the twisted Jacquet module means that you take the vector space V and you mod out by the subspace generated by the following vectors. You apply U to V and subtract the character of U times V. Okay, so that's a vector. You do that for all U and UO and V and V. You take the subspace generated by that. And so that turns out to be the right local version of it. And just as globally, we can say which Fourier coefficients, which averaging do you do the first time where you have averaged over little enough to get something non-zero. Locally, you can say when am I going to mod out by little enough that I get something non-zero. So I can ask which unipotent orbits O give a first occurrence of a non-vanishing twisted Jacquet module for representation of a p-adic group. And a non-vanishing twisted Jacquet module is analogous to a non-zero Fourier coefficient. And locally, there's a statement that's just like the global statement I mentioned for the Weil representation. All twisted Jacquet modules are 0, once again, except for that minimal non-trivial unipotent orbit. Okay, so there's a local version of the global statement that most Fourier coefficients of a theta function are zero. Okay, so those are the pieces that I wanted to talk about in this pre-talk, and that's information that we'll be making use of during the talk itself, where I'll explain this extended new theta correspondence. Let me just end by mentioning a few of the papers on the subject that I found very useful for theta series and the Weil representation. Roger Howe's classic paper, Theta Series and Invariant Theory, is a wonderful read, and I highly recommend it. And then there are two sets of notes on theta correspondences that I think are very, very useful, well written, and highly recommended. One by Steve Kudla and another by Dipendra Prasad. And if you go to the slides, which will be hopefully uploaded to the website for the seminar and then available to you, you actually can click on these links and you can go right to the author's web pages where you can actually access those articles. Okay, for metaplectic automorphic forms and covering groups, and in particular these higher covering groups, Peter McNamara has a very readable paper which sets up these groups and then describes some basic representation theory over local fields for them. So that paper is also referenced, and again, the link will take you to the archive version of it. And then there's a whole volume of asterisk about this with a very nice paper by Wee-Tek Gan, Fan Gao, and Marty Weissman called L Groups in the Langlands Program for Covering Groups, a Historical Introduction. So there are a lot of references about metaplectic automorphic forms and covering groups, but those are two that are particularly useful. And finally, for Fourier coefficients and unipotent orbits, David Ginsburg wrote a paper that I have read many times and find very useful in the Israel Journal in 2006, which relates unipotent orbits to automorphic representations and has some very fundamental conjectures, and also explains a lot of the constructions. The standard book, which is a nice thin book and very well written to learn about unipotent orbits, is this book by Collingwood and McGovern, Nilpotent Orbits in Semi-Simple Lie Algebras. And then lastly, let me mention a paper that I wrote with David Ginsburg that's actually just wrote a year ago, and it's going to appear in a volume and it's on the archive, called Dimensions of Automorphic Representations, L Functions and Liftings, which in some ways a little bit updates David's 2006 paper, expands it a little bit, and also has a certain amount of exposition, which might be relevant and of interest. Okay, so thank you very much, and I look forward to seeing you at my talk.